Welcome to the 7th student. Today we're looking at D2.3 Water Potential in IB Biology. This is a short one, unfortunately a bit harder for the ones doing HL as always, but let's get cracking. So first we have solvation. Now what does this mean? Basically it just means that water is an excellent solvent. So remember, water is polar. This is recap, but just in case anyone doesn't remember. So we have oxygen, and oxygen has a partial negative charge, and the hydrogens have a partial positive charge. So what does it mean for something to be dissolved in water? Well, that process is called solvation. And basically what happens is that water surrounds and interacts with the solute, like you can see here. So we say that water dissolves polar molecules and ions. Why is that? Well, polar molecules dissolve because of hydrogen bonding between the water and polar regions of the solute, right? So those partial charges between the solute and the water allow it to dissolve. In the case of ions, it's due to electrostatic attraction, which is basically the same thing. But in ions, right, we have cations, so for example, sodium, and that's positive, so it's attracted to the oxygen pole of water. And then we have anions, such as chloride, which is attracted to the hydrogen pole. It's still the same thing, right? It's just that in ions, we have full charges, so it's full charges being attracted to the partial charges of the water, whereas with polar molecules, it's partial charges in the polar molecules being attracted to partial charges in the water. All right. So what happens then is that water surrounds the solute, be that a polar molecule or an ion, and these interactions allow water to form what's called a hydration shell. Okay, key term to remember. So they form hydration shells around each ion, keeping them dispersed in solution. So this is what prevents solutes from aggregating and precipitating out. It is crucial for maintaining the solubility of ions and the polar compounds in systems such as the cytoplasm. Okay, great. So osmosis. Hopefully you know what this is by now. It's the net movement of water across a semi-permeable membrane from a hypotonic solution, meaning a lower solute concentration, to a hypertonic solution. All right. So key terms. Hypotonic is a lower solute concentration. Hypertonic is a higher solute concentration, and isotonic is when there's equal solute concentrations. In an isotonic environment, there's going to be no net movement. That doesn't mean there's no movement, okay? There is movement, but it's just the same in both directions. There's a dynamic equilibrium. However, if a cell is in a hypertonic environment, what's going to happen is that water is going to leave the cell more than it enters it, so a cell can shrink. And in a hypotonic environment, water enters the cell more than it leaves, so the cell can swell. All right? Cells cannot change osmosis itself. Like, osmosis is always going to go from a lower concentration to a higher concentration. But what they can do is they can adjust the speed of osmosis through aquaporins. What are aquaporins, you might ask? So aquaporins are these proteins that can be embedded in the membrane of the cell through which water can flow. So basically they alter the permeability of the membrane to water. The more aquaporins, the more water that can go through. And then if a cell wants to control the direction, they have to adjust the solute concentration. As we said, they cannot change how osmosis works itself, right? So this has a lot of consequences on cells, okay? If we look at cells without a cell wall, for example, animal cells, right? Our cells, if our cells are in a hypotonic solution, water is going to enter the cell by osmosis. This can cause the cells to swell and even burst. That's called lysis. This is because there's no structure to resist the pressure of all this water coming in, right? However, in a hypertonic solution, water leaves the cell, so the cytoplasm can shrink, causing the membrane to wrinkle, and that is called crenation, okay? Another key term. Great. Now, what about in cells with a cell wall? Well, if they're in a hypotonic solution, again, water enters, but here the difference is that because you have a cell wall, right, the plasma membrane, is going to push against that cell wall because pressure is building up because of the water. That's called turgor pressure, and we say that the cell becomes turgid, and that is actually a healthy state. So this is a good thing for cells with a cell wall, such as plant cells. If these cells are in a hypertonic solution, okay, water is going to exit. So the cytoplasm shrinks again, and the cells become flaccid. And this is what leads to wilting, right? In a plant, when you see it wilt, it's because of this. It's because of not enough water. However, if there's enough water loss, right, the plasma membrane will actually pull away from the cell wall, and that's called plasmolysis, often irreversible and fatal to the cell. So quite a serious thing. Okay, so what is an application of this? Okay, in medicine, so we need to use isotonic solutions to match the solute concentrations of cells. This is to make sure that the cell doesn't swell or shrink. So that's why we use normal saline solution for most things, right? So for IV fluids, rinsing wounds, eye drops, organ preservation, etc. Okay, that's all for the SL people. Now let's move on to HL. So we're looking at water potential, and this has very much to do with the idea of osmosis, right? So water always moves from a higher to a lower water potential. Okay, this is the same way that objects move downhill to lower energy states, or if you throw something off a building, it's going from a higher potential to a lower potential. If you study physics, you'll know this. Otherwise, just remember that water moves from a higher to a lower water potential. So pure water at 20 degrees and an atmospheric pressure has a water potential of 0. That's important to remember, okay? And then when there's solutes, that lowers the water potential, okay? Because remember, water goes from low solute concentration to high solute concentration. So if you have a lot of solute, you have low water potential. And then high pressure raises water potential, okay? So this explains why water moves from a low to a high solute concentration. So in a hypertonic solution, the inside of the cell has a higher water potential. That's why the water moves out. In an isotonic, there's the same potential inside and out. And in the hypertonic, there's a higher water potential outside. Okay. So as I mentioned, this is another visualization of that. Solutes lower the water potential, right? Always, because basically the more solutes, right, the less likely the water is to leave because of the way osmosis works, right? And then pressure increases water potential when it's above atmospheric pressure, and it decreases it when it falls below atmospheric pressure. Why? Because at higher pressures, the water is more likely to leave, right? So that's why it raises the potential. So as you can see, solute concentration can only decrease the water potential, pressure can increase it or decrease it. So this is the formula that gives you the overall potential. So you have to take into account both. All right. And last thing, I know we've talked about this, but for some reason IB repeats itself a lot, and it's the effect of water potential on plants. So if the plant cell is in a hypotonic solution, okay, the potential of the solution is higher than the cell's potential. So again, water enters the cell, okay? It's exactly what we saw, but using potential, right? So the turgor increases. The turgor is the pressure, remember. The plasma membrane presses against the cell wall, and the cell wall counteracts that pressure to prevent lysis. So basically, the cell becomes fully turgid, right, when the potential of the cell equals the potential of the solution, and that's when there's no net water movement. And then we have when it's in a hypertonic solution, and that's when the potential of the solution is lower. So water leaves the cell, okay? And remember that leads to the cell becoming flaccid and possibly plasmolyzed because the plasma membrane detaches from the cell wall. All right, hopefully that makes some sense. Any questions in the comments? Let's do some questions. So what is the water potential of pure water, 20 degrees in atmospheric pressure? Hopefully you remember this because I said 5 minutes ago. As always, you can pause now to think, but I'm gonna give out the answer in 3, 2, and 1. It's 0, right? That's just how it's been set. There's no specific reason, okay? It's arbitrary, but it's been set to that, so you need to remember. What causes plasmolysis in plant cells? Again, 3, 2, 1. It's A. Why? Okay, so water loss due to a more negative water potential outside the cell. That's true, because in B, when it enters the cell, that leads to turgor, which is the opposite of plasmolysis, right? Then solute uptake has nothing to do with osmosis in this case. And then an increase in turgor pressure is what happens when water enters the cell, so B, right? So plasmolysis is actually when water is lost from the cell. Okay. And finally, last question, why does water prevent ions from clumping together in solution? Okay, so back to the first thing we looked at. 3, 2, and 1. Okay, remember it forms those hydration shells. Key term. Remember, write it down, write it down. Okay, it does not break down ionic bonds permanently. It does not evaporate easily. And it does not neutralize all charges on ions. Instead, remember, it forms that shell, like it basically encircles the ion, right? And that prevents the ions from joining together and clumping. Okay, so that's this topic. Any questions, leave them in the comments. And until then, I'll see you next week.